Hi, Assalamualaikum and very good day. Welcome back to our lesson today. So in the last video, I talked about the 18 electron rule for pi donor complexes. But I believe, even though there were not so many questions coming in to me, but I believe that some of you might have had some difficulties in understanding how electrons contributed per ligand is actually calculated. So I received this one message from a student, which is a very good on a very good note that she has made. So I would like to applaud her for being very proactive and advanced in understanding this particular chapter. So on my part, I would like to revisit this particular subtopic again. So hopefully you can pay more attention and we can get something new out of this lecture. Now, if you have the book from Doctors of any advanced organometallic chemistry book, it is very, very good. But if you don't, then it's okay. We can always be dependent upon the lecture notes that we have obtained earlier. Now, look at this table 12.4 electrons counting for pi donor ligands. We have understood what pi donor ligands is, since we have learned about olefin complexes. Now, look at this. We have C2H4, this is your ethylene, so we call it dihapto. Why dihapto? Because two atoms attached to your metal, or two atoms coordinated to your metal. So how do we count that? You can see that we have only two atoms here in one structure of your metal, or of your ligand. So definitely two atoms involved in coordinating with your metal. Now look at the second one. We have trihapto for allyl, trihaptoallyl, but 4 electrons contributed. Why so? You see all 3 carbons attached to your metal. But how do we count the electrons? We have 2 double bond, 1 double bond, 2 electrons. So the total electrons contributed by trihaptoallyl is 4 electrons. Then moving on to the next one, we have tetrahaptobutadiene. So tetrahapto means 4 atoms attached to your metal. So 1, 2, 3, 4. But why 4 electrons? Because we have 2 double bonds. So 1 double bond, 2 electrons. So 2 times 2, you're going to get 4 electrons. Moving on to the next ligand, we have N4 cyclopentadiene. This is not N4. I'm sorry. This tetrahapto cyclopentadiene. So four electrons involved. Four atoms involved in the coordination. So 2 double bond. So 2 times 2, 4 electrons. And then we have tetrahapto cyclooctatetraene. In the previous video, I kept saying cyclotetraene. It was actually cyclooctatetraene. My bad. I'm sorry. So, or simply known as COT. So, it is tetrahapto. So, since it's tetrahapto, we understood that there's going to be 4 atoms attached to your metal. But why 4 electrons contributed? Because we have 1, 2, 3, 4 atoms. So any carbon atoms that you pick, you're going to get 2 double bonds. So 2 double bond, 1 double bond going to donate 2 electrons. So 2 times 2, you're going to get 4 electrons. Then moving on. Now for cyclobutadiene, we have tetrahapto, meaning all 4 involved. So all 4 with 2 double bonds going to be 4 electrons. So we call it this diolefin. Now next we have cyclopentadienyl. We have pentahapto, all 5 involved with 2 double bonds, so 4 electrons, and with 1 alkyl group or alkyl group. So the same thing for this one, pentametal cyclopentadienyl. It's gonna be giving you 6 electrons as well, assuming that you have 2 double bonds and 1 alkyl group. Okay. Now next moving on to the next ligand, we have pentahapto pentadienyl. All five involve 1, 2, 3, 4, 5. Well, two double bonds, and then we have one alkyl groups. We're gonna be giving you 6 electrons. Next, we have benzene, 3 double bonds, 6 electrons. Tropylium, all 7 carbons involved with 6 electrons. 3 double bonds, so 6 electrons contributed. And we have cycloheptatriene. This is hexahapto. So 6 electrons involved, even though we have 7, but only 6 electrons involved, 6 carbons involved. 1, 2, 3, 4, 5, and 6. So within the 6 carbon, we have 3 double bonds, so 3 times 2, 6 electrons. Cyclooctatetraene, or COT, COT, 6 electrons contributed as well, because 1, 2, 3, 4, 5, 6 electrons involved. So for every 6 atoms involved, you have 4, you have 6 electrons. Okay, I hope you do understand now why we can get such number of electrons contributed by each ligand. Now moving on to the second part, would be a cyclopentadienyl complexes. So we know this can be denoted as CP. Your cyclopentadienyl can be easily losing the proton, so it will be a cyclopentadienyl anion with negative charge. So this cyclopentadienyl anion can form a complex. So the most famous one, we call it ferrocene. So pentahapto with your cyclopentadiene. So cyclopentadiene lost one proton, becoming cyclopentadienyl anion. Okay, so that's why it is negatively charged. Now we're going to learn what ferrocene is. So it is orange solid, melts around 170 degrees Celsius with sublimation. So can you tell me what sublimation means? What do you understand about sublimation? I'm sure if you have taken the general chemistry, you have learned this. And it is 6 electrons of ligand, as we have discussed earlier. It is diamagnetic. So can you tell me what is diamagnetic based on your understanding? Easily oxidized to blue, okay, with positively charged, having one unpaired electrons, easily oxidized with one unpaired electrons, meaning before it is oxidized, it must not be having any unpaired electrons. In solid state, the configuration is staggered sandwich configuration. In gaseous state, it's gonna be eclipse configuration. So meaning it can rotate very easily because the energy barrier is only about 5 kilojoule per mole. So from solid to gaseous state, the configuration change from staggered to eclipse configuration. Okay, so from this diagram we understand there is a difference between these two diagrams. I hope you do understand how to draw solid ferrocene and how to draw gaseous ferrocene. This one eclipse, this one staggered configuration. So from the X-ray structure, it reveals that the structure is very symmetrical, highly symmetrical. So all hydrogens are identical. So all protons are identical. So when we run proton NMR, we are going to get only one signal because all identical. Okay. So researchers have produced and still producing the cyclopentadienyl and these metal complexes with CP as a ligand are better known as metallocenes. Okay. So we know that your cyclopentadienyl anions and ferrocene contain 6 pi electron ring. Okay. So that's why it can easily undergo electrophilic substitution, just like your benzene. If you still remember how benzene can react with some other chemicals through electrophilic substitution. So we can always replace hydrogen with metal. For example, we have seen this C5CH3 Okay, so all hydrogens are replaced with your metal, and this ligand is very common, and the symbol is Cp asterisk. So Cp complexes common because Cp rings can bend back to make orbitals directly available for bonding to other ligands. Meaning, if you notice just now we have a few complexes. Even though your complex is attached to your Cp ligand, but at the same time your metal can still have some other bonds with some other ligands like Cl or carbonyl, for example. So that's why it says your cyclopentadiene anion rings can bend back to make orbitals sterically available for bonding to other ligands. Okay. Now, you can find this application where we can measure blood glucose levels quickly and strictly and simply using an exact tag. So it takes around 30 seconds for us to read the blood glucose, to know the sugar content, the glucose content in your blood. So actually the presence of ferrocene will help facilitate electron transfer from glucose and glucose oxidase. Okay. I'm going to be giving you a handout later on cyclopentadiene ligand. So far, what had we learned? First, I talked about 18 electron rule for your pyramidal ligands, olefins, diolefins, and why certain ligands can contribute only 2 electrons, and why certain ligands can contribute up to 6 electrons. And the second part of my lecture was on cyclopentadiene. It is actually originated from cyclopentadiene, losing one proton, becoming cyclopentadiene anion. And then without ferrocene. Ferrocene is actually the most common example and mostly synthesized compound from Cp ligand together with your iron. And we talk about a bit on the state configuration in the solid state and also eclipse configuration in your gaseous state. Okay. Last but not least, we talk about the application of ferrocene, where it has been used to measure glucose in your blood because it does facilitate the electron transfer between glucose and glucose oxidase. So that's all for now. Thank you for your attention, and please answer all the questions in the Padlet. Thank you very much.